Hello everyone, I'm Quan Gan, and I work with the Gold team in LASP at CU Boulder. Today, I will present some most recent Gold observations of quasi-secondary waves coupling with the atomic oxygen Nightglow in the ionosphere. Here's the quick outline. I would like to start by a brief introduction of wave coupling in the atmosphere and an ionosphere system. And from there, I will switch to a quick introduction of Gold mission and instrument. The crucial results are from a case study, so in which you will see the 16-day oscillations in the Nightglow during 2018-2019 SABER event. This schematic adapted from decadal survey overviews the wave coupling in the whole atmosphere and its impact on the ionosphere. In the lower atmosphere, very briefly, so we can see the small-scale gravity waves and the global scale tides and planetary waves. Tides are driven by the solar heating absorption of water vapor in the troposphere and ozone in the stratosphere, as well as the latent heat release associated with the convecting system in the tropical region. Planetary waves usually has a typical period of 2 to 20 days, and solar wave number 1, 2, and 3. A large subgroup of planetary waves is so-called Rossby waves. Theoretically, Rossby wave is a resonant wave, so that means any sources with resonant frequency can trigger Rossby waves in the lower atmosphere. And some typical Rossby wave includes quasi 2-day, 6-day, and 16-day waves. After wave generation, it propagates vertically in altitude, and usually gravity wave and tides can propagate across mesopoles and drive the variabilities in the thermosphere and ionosphere directly. The rest of waves are mostly dissipate and breaking in the mesopoles region and drive what is so-called turbulent mixing, so which can transport constituents between the middle and upper atmosphere. And the turbulence mixing is typically parameterized by the eddy diffusion in a general circulation model. So in this piece of works, we will focus on the variabilities in the ionosphere associated with planetary waves from below. So now we come to the Gold mission. Gold mission flies a far ultraviolet spectrograph viewed as LASP. From the picture on the left, so you can see the Gold instrument on board SES-14 communication satellites. The instrument has been deployed to a geostationary orbit at 47.5 degree west longitude, which is right over the mouth of the Amazon River. And in the picture, you can also see that the instrument has 2 identical channels, which enables a flexibility that one channel can do the normal scaling, while the other channel can do some sorts of campaign observations. And now we come to the animation on the right, so which is called the image cube simulation made by Dr. Stan Solomon using his global Aglo model. And from this animation, so you will get an idea of how Gold instrument should take spectral measurements from the space. And first of all, we see the entrance slit scan the northern hemisphere from the west to the east. And in day side, we see where the spectrum comes out. But right across the terminator, everything goes away except 1356. After northern scan, the slit scan back over the southern hemisphere from the east to the west. Accomplishing such a global scan typically takes 30 minutes by one channel, but if we use 2 channels to scan the disk simultaneously, the cadence can go down to the 15 minutes immediately. In the night side, the 1356 emission is mainly from the recompilation of the F region and ionosphere, and it's a very good proxy of the electron density in the F region. It's also the data product we have been used for this small piece of work. As mentioned previously, that the goal of this work is to look for the periodicity in the ionosphere associated with planetary waves from below. As such, so we have been looking at the northern hemisphere winter time of 2018-2019, so which is December 2018 through the February 2019. And the plot on the top is the Zolo range and the Zolo mean temperature as function of time. at 60° north latitude and 30 kilometers. And right after the day 22, and we see the temperature increase by 15 to 20 Kelvin over a short period of time. And in the meantime, the solar wind decreased dramatically, and around day 35, it reversed from the eastward to southward. The behavior in the temperature and the solar wind are consistent with a well-defined SW event, so which is the major SW event. And next, we come to the gold 1356 nanometer Nightglow. And what you see, the bottom left is the gold image in the geographic coordinates. And out of there, we see the two crests of the EIA region stands out, and it stretches from the South America all the way to the Atlantic Ocean. And the plot on the right is the same image, but in the magnetic coordinates. And from there, we see the two crest regions are located at around plus 10 degree in the north and the minus 15 degree in the south. Since we have confirmed the SW event in the Northern Hemisphere stratosphere, and during which so usually enhanced planetary waves, especially the long period planetary waves, will get enhanced. So the question is that what kind of the periodicity we can see from the ionosphere. The top plot is the brightness as function of magnetic latitude and the time. The time span are the same as the previous plot. And in the two EIA crest regions, we saw the brightness shows quite a large variabilities over the whole period. And we further performed the principal component analysis to identify the periodicity in the brightness. And it turns out that the first two principal components that are EOF1 in panel D and EOF2 in panel G accounts for the largest part of the variability. And EOF1 primarily describe the variabilities in the crest region. And EOF2 also describe the variations in the crest region, but note that the variations are out of phase between the northern and the southern crest. Now we come to the time sequence of EOF1 and EOF2 along with their wavelet spectrum. And very quickly, a prevalent 9 days oscillations has been confirmed from the wavelet spectrum, while in the EOF2, a prominent 16-day oscillations has been regularized by the wavelet spectrum. If we look back to the EOF2 time sequence, we see there are three or four peaks and troughs over this period. The 16-day oscillations is of particular interest to us because the period is very close to a period of the Rossby waves. Since we are talking about the variability in the ionosphere, so which could be driven by either forcing from above or forcing from below. So here we have a closer look into the forcing from above. We use the KP and F-chan indices. The blue curve is the KP and the red curve is the F-chan. And from the wavelet power spectrum, we see that the KP is dominated by a 24 days oscillations over the first 30 days, as well as persistent and predominant 9 days oscillations in the geomagnetic activity. And we thought that this 9 days oscillation is probably the source of the 9 days oscillations in the brightness between the day 10 and the day 30 in the EOF1. Regarding the F10, so we only see a 24 days oscillations. So from this diagnostics, we can say either KP or F10 doesn't present 16-day oscillations, suggesting that the 16-day oscillations in the ionosphere is not the result of the forcing from above, but rather is very likely connected to the forcing from below. And now we use the same temperature to further trace the wave activities in the mesosphere. The plot on the left is the temperature perturbations as a function of longitude and time at latitude 40 degree north and height 8 kilometers. And from this plot, we see the significant westward propagating pattern with solar wave number 1. And then we pull out the time sequence at a specific longitude That's what you see, the blue curve in the right in the panel B. With the wavelet analysis, we can see a prominent 16-day oscillations can be confirmed. The red curve superimposed is from bandpass filtering with the cutoff periods of 14 and 17 days. And we see definitely there is a 16-day, quasi-16-day oscillations in the mesospheric temperature. And the crucial point is that, so comparing the 16-day oscillations in the mesosphere and 16-day oscillations in the ionosphere, they shows a very high temporal correlation. So here is the last plot, which is the brightness residues from the northern and the southern crest. And first of all, we see the orange curve is the northern crest, and the blue curve is the southern crest. And we can see that there's a prominent 16-day oscillations in both the northern and the southern crest. And over the first 30 days, the amplitude goes up to the 10 Rayleigh, and it accounts for the pretty much 50% of the background. The dot line is the percentage difference. And the crucial feature is that the oscillations between the northern and the southern crests are in antiphase, which we believe that indicates the crucial coupling mechanisms. So now we give a little bit of discussion on the driving mechanisms. There are three mechanisms in the waiting list. The first one is the emission dynamo modulation, which refers to the planetary wave or tides interact with the emission dynamo rings and generate a polarization electric field and further modulate the vertical ion drift and the averaging ionosphere. If this mechanism played the leading role, so we would expect a more symmetric oscillations between the northern and the southern crests. But in the reality, the northern and the southern, or the oscillations in the northern and the southern crest are pretty much out of phase. The second, that means even if the emission dynamo modulation play a role in transmitting the 16-day periodicity, is not the exhaustive scenario. And the second mechanism is called modulation of averaging field line rings. It gives the scenario that planetary wave, first of all, modulates the tides in the middle hemisphere, and afterwards, the tides continue to propagate into the F region and modulates the field line rings, moving the plasma along the magnetic field and producing the oscillations in the plasma density. For our specific case, we suggest both two mechanisms should play a role in transmitting the 16-day periodicity from the middle hemisphere into the ionosphere. And the last mechanism is so-called mixing effect due to wave dissipation. From the observation point of view, so one can confirm whether this mechanism works or not. But from the modeling, probably so we can give a further elucidation in the near future. And here's the conclusions. I'm not going to repeat all the points, so which should have been covered previously. This work has been published in a JGR special connection. So from where, so one can not only find this work, but also a bunch of work that have been done by Gold team. If you have any question regarding this work, so feel free to contact me through this email. Thanks very much.